about joint work with Sergei from Australian National University, and we'll be talking about two-dimensional integrable models of statistical mechanics. And for simplicity, let's take the square lattice. Okay, so there are three different types of model I'd like you to acknowledge. They depend where you assign the local Boltzmann weights. So you can assign local Boltzmann weights to the vertices, faces, or edges. So, well, in the first case, the fluctuating variables, which traditionally called spins, but they are not spins. In our case, it will be just integers, assigned to the edges of the lattice, and the Boltzmann weights depend on the configuration of four edges surrounding the vertex. So in the second case, the spins are at the corner of the face, square face, and the Boltzmann weights assigned to the face. And the third case is the simplest one, so the spins interact through an edge, like an Ising model. So we call this case an Ising-type, or edge interaction, or Ising-type model. So what about integrability? Oh, we know a lot of models of this sort, of all three sorts, but we know that integrability, the first and the second type, is the Yang-Baxter equation. And for the third type, for the Ising type, it's usually Zeiger's stand triangle. Okay, so what do we know about Yang-Baxter equation for vertex and IRF, interaction around the face model, which are related by vertex face transformation, so they're closely related. We have quantum group classification, which covers most of the known model. So the quantum groups, and so in particular we know infinite series of trigonometric and R matrices, which are related to evaluation representation of affine here. Okay, so today we'll consider the simplest case of the quantum group UQSL2 hat, affine quantum group, and the standard R matrix here will be this R matrix, lambda S1, S2. The S1, S2 is just highest ways or spins of the two evaluation representation of the affine, this affine algebra. And so that's the definition. You take the universal R matrix and evaluate, specialize it to this representation.
So you are considering finite dimensional representation?
Highest weight representation.
So also infinite dimensional highest
Yes.
weight.
So it's here. So for generic value S1 and S2, so that corresponds to infinite dimensional representation. So when S1 or 2 is 2, when S1 S2 are half an integer or integer, the model admits finite dimensional reduction. In particular, the six-vertex model, usual six-vertex model, S1, S2 is 1/2. It's two-state six-vertex model, which is included here. Well, so we're talking about, so the six-vertex is spin 1/2, but the higher spin R matrices and the constant was developing through the 80s by many people, like Fateev Zamolodchikov, Spin 1, and other models. Many people contributed. So, what? So, Yang-Baxter equation covered this case. But what about star triangle? Well, Yang-Baxter equation in the vertex or IRF form is just associativity condition for co-multiplication in the quantum group. So it satisfies the, well, by definition, universal error matrix basically satisfies Yang-Baxter equation by definition. So, well, star triangle relations not entirely natural here. So, on the other hand, if we have an Ising-type model, for example, Ising model itself, or another Potts model, which is converted into the vertex or IRF model by various, what is known as statistical mechanics, decoration transformation. We take not just one edge, several edges, glue them together and can form, well, one particular transformation which I explained called star square transformation. We take, so given an Ising-type model, we can convert it to the vertex form or IRF, interaction round the face. But that's one-way street. In general, we don't know how to go, given the arbitrarily integrable IRF or vertex model. Could we convert it to the Ising-type where only two-edge interaction? So the answer is no. For example, for the high-spin six-vertex model, could we convert it to the Ising-type model? That's the question. Well, as I said, you just take the universal matrix, which you more or less known for this particular case, specialize it to, well, how to calculate that matrix. Let me discuss how to calculate it. Actually, it's not easy. Even you start with this definition, or there may be different way. For example, the spectral decomposition. Jimbo once wrote, so you use the group symmetry, Casimir operators. So use Clebsch-Gordon coefficients, and you can write the expression for any matrix of this type as a sum, the product of Clebsch-Gordon coefficient and some spectral function. Each Clebsch-Gordon in this case contains one summation, so two Clebsch, two summations, and spectral decomposition. So three summations. We can write this formula with three summations, but it's inedible. So you can take maybe one summation, you form one, but still you don't see anything. So, and nobody actually, because somehow that was known for many years, for maybe 20 years, nobody was, until recently, could write a sensible formula for this matrix. And that was done by Mangazeev. But he used new algebraic structures. He used a hidden algebraic structure between quantum groups. Let me tell you what. So the three-dimensional generalization of the Yang-Baxter equation called tetrahedron equation. And there are some three-dimensional integrable models and solution of the tetrahedron equation. And that particular model, six-vertex model, is just a two layer case of three-dimensional model. So there is a three-dimensional model, which is more complicated. If you take n layers, it will be related to SLN quantum group. So n becomes the third dimension. So, and using this additional structure, Mangazeev managed to write down a very simple formula, not entirely simple, but one summation, which is a basic hypergeometric series phi 3, 4, not 4. Okay, so for the start, let me explain how to convert the conventional two-state six-vertex model into the Ising-type. What do we do first? First, we list all vertex configuration. And we list in two forms, two equivalent forms. First is the edge configurations. So you see the edges, all of thin edges. There are 6 configurations. So the spin 0, spin 1. Or the second is as so-called solid-on-solid model, where you assign integer variable to the face here, and if the edge is bold, and you move from here to here, from right to left, the height of the solid-on-solid model increase. So increase this way. So we have two combinatorial restrictions of the 6 vertex configuration.
It didn't increase the third time.
Right.
When you move around, there must be some other rule.
No, only this. This increase, this increase, this increase.
Like this.
This increase. So increase from left to right, from bottom to top. So, and everything. So there no increase here, no increase here, but increase here and increase here. Okay, so that's completely equivalent. So they assign Boltzmann weights, omega 1 to omega 6. So I'll consider the case when these two are the same for simplicity. But for periodic boundary condition, these two occur only in pairs. So the only product is significant. Okay, what we do? So that we take solid-on-solid formulation, that's A, B, C, D integers. Okay. And we convert it to the, go to the dual lattice, place the center of the faces by the sides of the dual lattice. So we go from solid-on-solid to interaction around the face. So these integers surround the face, they interact. So we got yet another formulation. And now, these Boltzmann weights is represented in this way. So I introduced a central spin here, which is also an integer, and two spin interactions, which are denoted Wi, where I goes from 1 to 4, and they depend on the differences, And the differences are calculated according to the errors. So this one, W1, A minus N, A minus N. The error from the first, the arrow pointing to the first one. Okay, and so I require that when the difference of spin is negative, this Boltzmann weights is 0. They are chiral. So not symmetric with respect to the reflection. So, and I wrote down that sum. So you remember, if you look at these pictures, so these spins here, everything will depend on differences. So one of them here we can set to 0. So then the maximum here will be +2. So we have to work in the range of 0 to 2 to come, because everything depends on the spin differences. Okay, so, and this restriction of the summation here, they just come from that vanishing condition. So you can verify, even taking the piece of paper and the pen, that these 6 weights of the 6-vertex model are reproduced if you take these expressions for the weights. So there is additional vertical interaction, V and V minus 1, but they're not very important because they cancel if we stack the neighboring vertices on the list. So, but they appear here. So more or less they are arbitrary. And but the ratio go in the expression. So that's it. So we have reformulated 6-vertex model as an Ising-type.
So it's a bit confusing. So in some cases W3 is just a number, and then some other is a function, right?
Where W3 is?
On the right hand side of this third line from the bottom, there is W3. Without, no, below. Right. To the right. To the right. Above a bit. Above.
This is omega.
Third
Omega.
line.
Omega.
It's omega, not.
It's omega, and on the
It's
left hand
omega.
side
It's not W.
Yeah.
It's omega.
So these are 6 vertex weights.
Yeah. Ah, oh, okay. I see. So.
That's omega.
It's okay.
Well, it's similar, but not the same.
And the arrows are always fixed. The arrows
Yeah.
just right.
Arrows fixed. Okay, so.
Well, how it works for Karl-Potts model? It's also dependent on differences or not for Karl-Potts?
Karl-Potts depend on differences, but and depend on the sign of the difference. It's chiral as well.
It's chiral.
Chirality is, for example, for the Potts model, it doesn't, conventional Potts model, it doesn't depend on the sign of the difference. Okay, so after this exercise, so let's define a more general model. So do not completely forget what I said, but what I said, consider a square lattice drawn diagonally. Okay, here the sides, it's here, shown by open and filled circle. Okay, and some additional lines which alternate their direction. They usually called rapidity lines or spectral parameter lines. And also, so the spectral variables, and so we have placed an integer spins. And if you look carefully, but probably it requires some time, but you trust me, there are only 2 types of mutual configuration of the bold edges and thin rapidity line, where they all point to the same directions, like this, or like this. here you see, this one goes from here and this from here. But for this one, from here and from here. So the blue one is like this, and we assign them the Boltzmann weight, which is given by this formula. So it depends. So the thin line carries spectral variables, x and y. So it depends on x divided by y here, and the function v. It depends on spin difference and spectral variable given by this formula, where that's called Q Pohammer symbol. Okay, that's the definition. And according to this definition, V with negative n is 0, identically. Look, but here it's in denominator. So if the spin difference will be negative, that will be infinity. Fortunately, that will never happen, and I explain you why it never happened. So we continue our definition of the model. And so we put the boundary condition on the spin. We say that spin will increase, not increase, do not decrease. So in this way, so A2 is greater or equal to A1, and so A3 is greater than A2, so that. Okay. And similar, this spin B1 is greater or equal of A1, and so on. Okay, so after that, the careful analysis shows that this dangerous configuration where this red line has a negative spin difference just do not appear. Okay, so, and the partition function is the sum of all spin configurations. So, and we call them admissible if all spin differences are non-negative. It's a complicated calculation. You really realize this vanishing condition, and so, and you can exhaust all configuration, and these admissible configuration are only configurations which have non-zero Boltzmann weights. So you take the product of edge weights. You can add also boundary field factors, as usual, and so that's a definition of the partition function. Well, basically nothing complicated. You just take all the configuration there. Boltzmann weights is non-zero. Okay, so go further. With a spectral variable line, and we expect to have that's integrable model, will be integrable model, and that is a transfer matrix. So that what the matrix synthesis here, multi-indices, and they form a two-parameter commuting family when these axes are fixed, and y1 and y2 can be varied. How do we know this? Okay. What's the integrability condition? The integrability condition is the what is called star relation. So if you take this picture, which is given here, take this picture, you can verify that it is the same. How you prove it? It's not trivial. But fortunately, it has been done by Sears for us. It's follows from two Sears transformation for the corresponding. That is phi for.
Star triangle relation.
Sorry?
Star triangle relation. If you have star triangle relation, there's a problem.
Yeah, if you have star triangle, but we don't know about star triangle. We explore what we can get. So certainly this relation is simpler than Yang-Baxter equation. So now I tell you how it is all related to Mangaziev's R matrix. Okay? You take out W, which I showed here. It depends on A, B, C, D of the corner spins. Now form the differences. Everything depends on the differences, and we take A1, A2, and that is our matrix of the six. High spin R matrix of the six. Okay? So, and the ratio of these spectral variables x prime divided by x is related to S1. And so basically what I introduced is Mangaziev's R matrix, some trivial. And we know from the construction, and Mangaziev proved this, it satisfies Yang-Baxter equation. So that will be Yang-Baxter equation for that W. So it's the same quantity, just a different formulation in terms of the vertex indices or phase indices. So we know it satisfies the Yang-Baxter equation, but this relation is much more complicated than this star relation. So, yes, we got a simple relation which is formulated in terms of two spin weights, Ising-type weights. But as Grigory correctly questioned, is there star? So how to prove? How to prove? Oh, let me show you how to prove. Now, using star relation, how to prove this Yang-Baxter equation. You take four W's, that's one of them, here. That's another one, and that's the third one. Okay? And some of the edges cancelled out, because we have them in denominator, and for example, this one is cancelled. So we look at the picture and see that in the middle we have ingredients of the star-star relation. We apply star-star relation here. You see something changed. Then go identify the second, the third. We apply it consequently and arrive to the right-hand side of the Yang-Baxter equation. So we applied it, but it's probably it was known. Of course, it was known before, but I'm just explaining that star-star relation implies Yang-Baxter equation. Okay, what about star triangle relation? It's conceptual to understand. Do we have something? We have to find the simplest relation, and possibly we could have. Yes, there is. But to formulate this relation, we need to introduce an additional Boltzmann weight, which is W. It depends on two spectral variables, on spin difference, x and y, and given by this formula. Previously, the weight V, we have Q squared here. Okay. Here, that's arbitrary variable. So V is when we put Q instead of Y, the previous. Yeah, and this way doesn't depend on doesn't have difference property. Right? So what we have, this way satisfies star triangle relation. How to prove? That has been done 200 years ago by Pfaff, very discovered by Schultz, and when, so that's the misprint.
There's no
No
H.
H. The first H is wrong.
Okay.
H method.
And
Schutz with one H.
Schultz. And the co-analog was obtained by Jackson 100 years ago, more than 100 years ago. So that is a 5-3 to summation formula. So Schultz found it in Q equal in rational case with gamma function. So beautiful. So let's come back to the R matrix formulation. So we have this given on ABCD, and we want to look at this as an R matrix with the age indexes I1, I2, quantum space, I1, J2, auxiliary space. Okay. And so if 2s2, s2 is half an integer, when there's a reduction. So the R matrix takes the block triangular form, and it splits into the finite dimensional matrix, where the indices run 2s plus 1, 2 plus 1 values, and infinite rest. Okay, still. Okay, so if we apply that reduction to the third space of the Yang-Baxter equation, we'll get what is called RLL relation. So the third space is two-dimensional. So the L1 and L2 become 2 by infinity matrices. It's 2 by 2. And the elements are operators which act in infinite heights, way the representation of UQSL2 without hat, without hat. And the matrix elements are given. Well, and that guy, R12, is our R matrix, Mangaziev's R matrix. In principle, if you know this, and that is known to everyone, that expression for the L operator, you could have calculated this formula by solving this relation. And if you, well, interestingly, the Mangaziev has commented on this. When he's got that expression, his expression, he verified that it satisfies this relation, and he said that, well, it reduced to some recurrence relation for the element of the this R matrix, which could be easily verified when you know the answer. But if you don't know the answer, it's not easy how to solve. Okay, so and now I explain you how to solve. Okay, and the trick is here, well, as Einstein told us, nothing depends on the frame of reference. Let's take the different bases in the vector space which support the representation of our quantum group. Basically, that is our L operator, and we can write it. If you introduce the while algebra, uv is equal to q squared du. That's the previous formula that we use. U is yes, Cartan element. Q to the h is diagonal, and v, which is appear here, where is it? Yes. F, yes. Yeah, it's here. That's the same formula with these notations here. So it's just the same formula rewritten with these notations. But now take different representation of this while algebra. Make q to the h, which is a Cartan element, not diagonal, but the shift order. Could we do that? Of course we can. Could we now solve the equation? And fortunately we do. And the answer is factorized. So it's the R matrix, the quantum space, auxiliary space, that's the indices, and the expression is given by this simple product. Is it surprising? Probably not. Sorry. If you look at this picture, definition of our model. Initially, we split the lattice into stars and worked with these stars. But the same model could have been defined if we are splitting lattice into the diamonds. And there are two different types of stars. So this one and this one, with the black centered star and white centered stars. Okay? But they are equivalent due to star relation. But equivalently, we could have split the lattice into the diamonds and got the same partition function. So that's what we did. Okay, so the exact relation between two R matrices is quite simple. It's some kind of discrete Fourier transformation or discrete Laplace transformation, I would say. So for those, because our conference, sorry, pressed the wrong button. Has quantum field theory in the title, I explain what has happened. Suppose you have consider one loop 4-point function in quantum scalar quantum field theory, where the propagator is G, say even function, and one loop diagram. The box is given by this factorized expression. Now make Fourier transformation of this box. So we have delta function of the conservation law, and for Fourier transformed quantity is exactly a star diagram if we introduce the momenta are given by these differences. So it's a trivial calculation. So it's if you have an R matrix, let's make Fourier transformation. It was complicated expression, but we made the Fourier transformation. It has become factorized. So what I wanted to show you, some pictures. So, and the structure which behind this factorization already manifests itself into the expression for the L operator. If the L operator written in this basis where Cartan element are shift operator, then all matrix element of the L operator of these IG indices will be A will be equal to A prime, or A prime will be A plus 1. And so we can factorize this expression in two free spin weights. That's one free spin weight, which depends on these two, and this, and the function V, which appeared, W, I would say, here, satisfy this Yang-Baxter equation. It's a more elementary equation which doesn't appear on the formula with quantum group. And so, and that's verification where we get the box diagram out of this calculation. So, what we can do next? What we can do next? We can construct everything. Now construct everything. And the whole theory of the six-vertex model, Baxter Q operators, Bazhanov, coordinate, and algebraic. By the way, Baxter Q operator will be just as so, like in the chiropods model. The Bazhanov, for those who know the coordinate Bazhanov, is the same formula you had for the six-vertex model, with one exception. In the six-vertex model, these numbers which give the position of down arrow cannot coincide because spin 1/2 inclusion principle. But for infinite dimensional representation, you have as many as you like. So otherwise, the expression doesn't change. 10 minutes. Okay, almost finished. 10 minutes for the question. Okay, so, well, could we generalize this construction? Yes, we can. For example, we already checked that for SLN, Perk, Schultz, unrelated Чередник, I would say, Чередник, Perk, Schultz are matrices. We can also construct an Ising-type representation. So the key element of this construction was the hidden three-dimensional structure. But this three-dimensional structure exists for all quantum groups. And this was demonstrated by the hard work of many people, and particularly not only for SLN, but for other quantum groups. So potentially we can reformulate all vertex model associated with quantized affine Lie algebra as Ising-type models. Thank you very much.
Questions?
What about elliptic R matrices? Did you check?
No.
Some?
Well, we didn't check, but
I mean, these hypergeometric summations that you are using, I mean, they are there. They have elliptic analogs. So,
so we didn't check, honestly. So there's something for you there.
great. Thank you.
Yes?
Maybe just a comment. So somehow this reminds me of this twin.
Your hand. first your hand, yes? Then I give you opportunity to very obvious, yeah?
He's the boss. Okay, let's settle it up.
Okay, go.
Thank you. So this reminds me of some paper on a 20-vertex model on a triangular lattice, first studied by Kelland, and then later on in '78 by, I think, Baxter, Timperley, and Ashley. So they found that this model also somehow factorizes onto Kagome lattice models, and then it becomes finally a Potts model on a triangular lattice, again, an Ising-type model, so to speak. And this structure here, where you start from somehow something a little bit complicated, and then it factorizes in the end, that looks like this is also what happens in this paper.
Well, I'm not familiar with that work, but I know that people did it for the Ising model, decoration transformation. So if you take, say, checkerboard Ising model, where you the coupling constant goes in checkerboard way, then you can convert it to the vertex free fermion model. So, but that part of knowledge was somehow gradually forgotten.
Oh, we can just
Okay.
maybe there's some.
Yeah. I would be happy to have a look.
So, all these very nice formula, star triangle and star and so on, I know they were also present when somebody studied SL2 spin chain in principal series representation, and for example they connected to Lipatow's Hamiltonian for Pomeroy BFKL model. And so, since in one of your last slides you were transforming and basically writing a piece of Feynman diagram in a sense, so would you say that all what you showed basically implied all that findings?
Yeah. You know that. So somehow the Lipatov stuff is related to what is called fishnet diagrams. It's not a representation of this class. It's a different representation.
My straightforward question indeed is if this stuff would coincide with the analog technology for fishnet, and the answer
yes, I think most of it will coincide.
But here you have Q deformation. There was no Q deformation. I don't know how important is that.
No. We have half infinite highest weight representation.
Yeah, but everything is
So
Q deformed.
there are no highest weight. So it's more.
I could make a comment on this. A long time ago, we started basically what Enrico mentioned. It was SL2C spin chain. There was no highest weight. Basically, my comment would be that the same construction we presented here, it works independently whether your representation has highest weight or not. So we started with an infinite-dimensional representation of SL2C group, so there's no highest weight. And then you could ask various questions like about R matrix, transfer matrices.
Yeah. I'm sure that is.
And
I forgot to mention. Yes.
Yeah, it's the same diagram, the same argument goes through, and you don't need presence of highest weight.
Okay, you don't need. So.
You need it only when you want to construct the beta ansatz, but for to prove all those relations, you don't need it.
For the relation, I agree that somehow it was known. Something was known.
Situation for cyclic representations, like in Karl Potts.
For the Karl Potts model, is the same. The same construction was known before.
No, I'm not saying simply with different supplementary dimensions. We have in field theory. I'm saying that in field theory, people run across those constructions, solving completely different problems in different fields. But actually, at the end of the day, what's good that what you're drawing is the Feynman diagrams. From my point of view, you finally figure out the Feynman diagrams are very useful.
I showed you the Feynman diagram. Yeah?
Well,
sorry. Okay, I wasn't done with it. Please.
So you get now the R matrix solution of the Yang-Bex equation from something simpler. So my impression would be it's less constrained, so there might be more solutions. Is Is that correct, or is it just an equivalence? Do we have more solutions or other integrable systems which are...
We do have, well, yes, there are some new solutions which are infinite dimensional, which are present in the paper, which I think didn't be before, which uses this new weights doubling.
Does it mean that you can extend the classification beyond, say, quantum groups, beyond what you get from the universal R matrix?
Yes.
Well, I haven't thought about this seriously. So, but what I don't understand, so in the quantum groups, there are no place for star triangle relation. So that means there are something maybe simpler, maybe more complicated, where you have more elementary structure, free spin weights and all that, and all the star triangle relations. So that is one thing which I was thinking, but I don't know the answer.
Yes. A question about the SLN generalization. I think there you need as a target space an n-1 dimensional lattice, I believe. And a related question, does it make sense to formulate Hamiltonians for these models?
I didn't understand the question.
You didn't? So for the SL2 case, you have to go up and down a line. I mean, in order to do, the A plus 1, minus 1, A plus 2, etc. So this construction from spin to height values. I mean, that in the SL2 case,
Yes,
which is rank 1.
SL3 you have the weight lattice.
Yeah, there you have a weight
And
lattice.
so you have some area on the weight lattice.
Yeah, so the weight lattice, right. So it's two-dimensional, and when you go up to SLN, then you have n-1 dimensional lattice, and so that generalizes in this way. And then the question, is it possible to formulate a Hamiltonian for these models? Is there a Hamiltonian limit?
Of course, of course.
And has it been investigated?
No.
No.
So the expression is written, you can formulate the Hamiltonian.
I have a question maybe related to Fran's question. So if you start with this Ising-type, actually you know nothing about quantum group whatsoever, right? So are there some hints that you will come to something related to quantum group?
Yeah, of course. What is called decoration transformation. You have elementary building blocks like Lego. You connect 4 pieces and you got a matrix. It's Jan-Baxter Lego.
You take your weights, which are 0 for negative.
Yes.
In principle, you could take them something like in Karl Potts. Would you come to the structure this way, in this case? To quantum group structure? Maybe not. Yeah. I don't know.
No, zero for negative is, no, actually it doesn't help. So what you do, you can put epsilon there. And small epsilon. And study the question by L'Hopital. So for all lattice configuration where epsilon go to denominator, you'll have epsilon in numerator coming from the other weights in a bigger power. So the answer is always negative to negative in our formulation. I don't know whether it answers the question or not, but it is. But Karl Potts is a different stuff. It's a cyclic representation.
Yeah.
You don't have highest weight or lowest weight. So it's,
Okay, maybe we thank the speaker again.